Good morning everyone, I'm Miss Lara and welcome to your basic calculus class. But before we start, let's have a little brain teaser first. Do you miss the Malolos mini forest? I bet you do. Let's assume that after a long quarantine, you have decided to walk from your house to the mini forest. The fresh air clears your mind and helps you think better. In order to get there, you first have to go halfway to the park. This portion of your journey takes some finite amount of time. Once you get to the halfway point, you need to walk half the remaining distance. Again, this takes a finite amount of time. Once you get there, you still have to walk half the distance that's left, which takes another finite amount of time. This happens again and again and again. You can see that we could keep going like this forever, dividing whatever distance is left into smaller and smaller pieces, each of which takes some finite time to traverse. So how long would it take you to reach mini forests? The problem is there are infinitely many of these finite sized pieces, so shouldn't the time be infinity? This is the dichotomy paradox of Zeno of Elea, or the paradox of cutting in two. From philosophical perspective, it's easy to agree with Zeno, but mathematicians have then realized that it is possible to add up infinitely many finite-sized terms and obtain an exact answer. But how? Let's think of it this way. Let's start with a square with an area of 1 square meter, then chop the square in half, then chop the remaining half, and so on. While doing this, let's keep track of the areas of the pieces. The first slice makes two parts, each with an area of 1/2. The next slice divides one of those halves in halves, and so on. But no matter how many times you slice up the box, the total area is still the sum of the total areas of all the pieces, which is 1 square meter. Now you see the logic of Zeno's dichotomy paradox. As the number of chops approaches infinity, the entire square becomes covered with blue. But the area of the square is just 1 unit, and so the infinite sum must be equal to 1. Now, what we are entering here is the concept of limits. In this lesson, we're going to consider functions of a single variable and study the behavior of the function as its variable approaches a particular value, focusing on illustrating limits of a function using table of values and the graph of the function. From our problem, we can say that the limit of the blue area as the number of chops approaches infinity is equal to 1. So we can write this like this. If we're going to let the blue area of the function be f of x, let number of chops be x, and the answer be L, then we can write this like this. And this can be read as limit of f of x as x approaches c is L, where c is a constant and L is a unique real value that f of x will approach as x approaches c. So to illustrate, let us consider the function and find the limit of x squared plus x minus 6 over x minus 2 as x approaches 2. In your first look in the given rational function, alam na natin agad na mag-undefined yung function at x equals 2, so that we will not let x equals 2. Instead, we're going to investigate kung ano mangyayari sa f of x habang papalapit yung x sa 2. To do that, we're going to use a table of values. So, kukuha tayo ng numbers na malalapit sa 2 pero mas mababa sa 2. Examples are 1, 1.5, 1.9, and so on. Then, by substituting values of x to the given rational function, we obtain f of x is equal to 4 when x is equal to 1. We'll write that value in the table and do the same with the rest. Now, observe the table of values. As x becomes closer and closer to 2, f becomes closer and closer to a particular number. What do you think is the number? Correct, f of x is approaching 5. On the other hand, we also evaluate f using values to the right of 2. So, kuha tayo ng numbers na malapit sa 2 na mas mataas sa 2. So, from the right, we can have 3, 2.5, 2.1, 2.01, and so on. Then again, substitute 3 and evaluate. So, we will obtain 6 by doing that when x is 3. So, do the same with the rest. Similarly, we can see that as x becomes closer and closer to 2, but this time galing sa kanan ng 2, f becomes closer and closer to 5 as well. We can say from here that the difference of the values of f and 5 becomes smaller and smaller as the difference of the values of x and 2 becomes smaller and smaller as well. So summarizing the results, we have the following conclusions. As x approaches 2 from the left, f approaches 5. And as x approaches 2 from the right, f approaches 5 as well. Now we call 5 as the limit of x squared plus x minus 6 divided by x minus 2 as x approaches 2. To further analyze the data, let's illustrate its graph. This is the graph of the function generated from Desmos, and we can see that the function is a straight line defined at every real number except 2. Kaya may hole siya doon sa x equals 2. So in analyzing a graph, to evaluate the limit of a function as x approaches a number c from the left of c, we must trace the part of the graph immediately on the left side of x equals c towards c, and determine the y-coordinate corresponding to the point being approached by f of x. On the other hand, to evaluate the limit of a function graphically as x approaches the number c from the right of c, we must trace the part of the graph immediately on the right side of x equals c towards c, and determine the y-coordinate corresponding to the point being approached by f of x. We will further discuss this topic on future lessons. But for now, let's have another example, but this time, this is a piecewise function. This looks a bit different, but the logic and procedure are exactly the same. Again, we start with constructing a table of values and take numbers approaching 4 from the left side first. So you can have any number you want as long as they are arbitrarily close to 4 and lower than 4. Since may mga sub-functions ang piecewise, dapat ang gagamitin nating sub-function sa pag-evaluate ay yung function na pasok ang x restrictions niya. For example, since 3.7 is less than 4, we are going to use the sub-function x plus 1 to evaluate f of x as at 3.7, which gives us a result of 4.7. Then, evaluate the rest and fill in the table. Now, let's take values approaching 4 from the right. So, ito yung mga values na napili ko. In this case, since all values are greater than 4, then we use the sub-function x minus 4 quantity squared plus 3. Then, upon evaluation, we can get the following values of f of x. Now here, you'll appreciate kung bakit ba natin kailangan kunin yung limit from the left side and from the right side. Bakit hindi pwedeng mamili na lang kung left or right? I want you to observe the two tables. You'll notice na magkaiba yung number na ina-approach ng function from the left and from the right. So, from the left, approaching 5 siya. And from the right, approaching 3 naman siya. In such cases, we can say that the limit of the function does not exist. Or in symbols, we write D and E. Bear in mind that we do not say or write that the limit of f of x equals D and E, because D and E is not a value. Hence, we say the limit of f of x does not exist. So generally, in evaluating limits of functions, we take values of x from the left of C and values of x from the right of C. The direction may be specified in the limit notation by adding a negative sign and a positive sign respectively. Furthermore, we say that the limit of f of x as x approaches C exists and is equal to the number L if and only if limit of f of x as x approaches C from the left and limit of f of x as x approaches C from the right both exist and are equal to L. On our next lesson, we're going to distinguish f of C from the limit of f of x as x approaches C. But for now, let's check comprehension. Thank you for watching. I hope you learned something from the lesson. So if you have any questions, feel free to message me or email me. But that's it for now. So see ya!